Welcome to another pharmaceutical calculation solve along. If you are in pharmacy school, then one of the things you should be proficient in is osmolarity calculations. And if you are in the United States of America, then you are likely to see osmolarity calculations on the NAPLEX board exams as well. So now in this video, we'll be taking a look at two interesting osmolarity calculation questions. And this video is actually part 5 of a 5-part series. So this is the last session in that series. And so if you'd like to watch the first 4 videos, I'll put links to those in the description and I'll put it in the card as well. Now, if you're watching this live, you could ask your questions in the chat. And if you happen to watch the replay, just leave your questions in the comments and I'll get to them as soon as I see them. So let's dive right into the first question. And the question says, calculate the osmolarity of a parenteral solution prepared by dissolving 3,000 milligrams of sodium chloride and 150 milligrams of potassium chloride in 500 milliliters of water. Round to the nearest 100, do not include units. So what you notice in this question, if you do a quick analysis, is that you have two components. Most of the examples we've looked at up to now always have only one component in there. So we will look at how you address these type of questions when you have two different elements or components in your solution and the right way to basically go through the solution. So what we want to do is recall the equation for osmolarity. And that will be milliosmoles per liter is equal to grams per liter divided by molecular weight times the number of particles times 1000. And so what we'll end up doing is we will use this equation, but we'll use it to find the osmolarity of the contribution from the sodium chloride, and we'll do the same thing for the potassium chloride. And once we are done, we'll then add up those two numbers, because osmolarity is a way you measure osmotic pressure, and osmotic pressure is a colligative property, which means that it depends on the number of particles in a solution. And so we can actually end up adding the different contributions of osmolarity from sodium chloride and potassium chloride to determine the osmolarity of the entire solution. So that's the overall strategy. So let's start off with the sodium chloride. And we're going to make use of this quantity. It's 3,000 milligrams. But notice that we have grams per liter, and our 3,000 milligrams is in 500 milliliters. So we need to do some manipulation. The first thing we want to do is convert the milligrams to grams. So you have 3,000 milligrams. 1,000 milligrams is 1 gram. And so you end up with 3 grams. But this 3 grams is in 500 milliliters. And we need grams per liter. So for thoroughness, we will set up a proportion to determine how many grams would be in 1,000 milliliters. We can actually just know that 1,000 is twice 500 and multiply by 2, but let's go through the full solution for completeness. So here we have 3 grams times 1,000 milliliters divided by 500 milliliters. And that gives us 6 grams in a liter. So we know this quantity. The molecular weight is the next thing we want to do. So molecular weight of any. So let me write that more legibly. So molecular weight of sodium chloride is actually 58.44. So this is one of those values which is actually good for you to memorize, because you would really encounter sodium chloride very frequently. So we found the molecular weight, or we know the molecular weight. Now we need the number of particles. For number of particles, we take the sodium chloride NaCl. If you put that in an aqueous environment, it dissociates to a sodium cation and the chloride anion. And your number of particles will be, you have 1 sodium and 1 chloride. So number of particles is 2. So we are almost there. And what we can do is actually determine the osmolarity from the sodium chloride. So we put all these values back into the equation. We would have milliosmoles per liter being equal to 6 divided by 58.44 times 2 times 1000, and that should be equal to 205.34. So we need to do a similar thing for the potassium chloride. Okay, so we'll do that on this side. So for KCl, we are basically going to repeat the same process. Okay, so this time around you have 150 milligrams, but it's also in 500 milliliters. So we'll do a quick conversion. 150 milligrams. We want to convert this to grams. So 1,000 milligrams are present in 1 gram. The milligrams cancel out, and you have 0.15 grams. But notice this 0.15 is in 500 milliliters. So we set up a quick proportion. 0.15 grams in 500 ml equals X grams over 1,000. X equals 0.15 times 1,000 divided by 500 milliliters, and you end up with 0.3 grams. We've already been given the molecular weight, so we don't need to do much there, but we need to determine the number of particles. So if you start off with KCl, potassium chloride, you put that in an aqueous environment, you would end up with a potassium cation and a chloride anion. So your number of particles is actually going to be the potassium cation and the chloride anion. And so you end up having 2 particles. So now we can put all of this information back into this original equation, and we'll have milliosmoles per liter being equal to 0.3 divided by 74.5 times 2 times 1,000, and that is equal to 8.05. So what do we do now? What we do actually is find the total osmolarity. Okay, so we found the contributions from sodium chloride and potassium chloride, but to determine the osmolarity of the solution, we can say total, and that should be equal to the 205.34 plus the contribution from potassium chloride, and that should be equal to 213.39, and that's because it said round to the nearest 100, do not include units. So that's how you actually address this type of a question. What are the key points or the takeaway message, the take-home message? Whenever you have multiple components, the strategy is to determine the osmolarity for each component, and then you sum them up. Okay, and always you want to make sure that when you're using the equation, it's always grams per liter. So make sure that your quantity is scaled up to the appropriate volume. So if it's in per liter, you're fine, But if it's in some other volume quantity, such as 500 ml or 250, you want to make sure that you always scale it to grams per liter. Okay, let's take a look at another question because I don't see any questions in the chat. All right, so this question says 10% dextrose with molecular weight 180 and 0.9% sodium chloride injection USP is supplied in a 500 milliliter ViaFlex plastic container. What is the osmolarity of this solution? Round to the nearest 100. Do not include units. So this is very similar to the example that we just did, and we just notice one quick difference, and that will have to be with the dextrose. So when we go through the solution, we'll just notice the difference. Dextrose is a non-electrolyte, so it would not dissociate, and the number of particles in that scenario will be 1. Okay, but let's start off. We'll go with the equation. So milliosmoles per liter is equal to grams per liter divided by molecular weight times number of particles times 1000. So this equation you want to have stenciled on your mind. You need it very frequently. So we can start off with dextrose as our first quantity, and let's talk about, we already have the molecular weight, so the next thing we need is particles, and like I mentioned, the number of particles for dextrose is 1. And the reason it's 1, once again, is because dextrose is a non-electrolyte. It will not dissociate. Another example of a non-electrolyte that you may see commonly is mannose. And so just keep that in mind. So number of particles there is actually 1. The one thing that we need is the quantity that goes in the grams per liter section. And we get that from using the information of the 10%. That's the percentage concentration. So what that will mean, 10% implies that you have 10 grams of dextrose in every 100 milliliter of solution. But since we need grams per liter, we need to determine how many grams will be present in 1000 ml, which is a liter. So we can go ahead and actually solve for X, and X will be 10 grams times 1000 milliliters divided by 100 milliliters. So the ml cancels out, and you actually end up with 100 grams. So this 100 grams is what is present in 1 liter. So we can go ahead and put in the values in the equation. So milliosmoles per liter is going to be equal to 100 divided by the molecular weight of dextrose, which is 180, times the number of particles, which is 1, times 1000. So if you do the math, you end up with 555.56. But we don't stop here, because we have sodium chloride also present in this solution. So we need to figure out or determine what the osmolarity is for sodium chloride as well. So we have NaCl, and the number of particles here will be slightly different. It will be 2, because when you put NaCl in an aqueous environment, it dissociates to the sodium cation and the chloride anion. And your number of particles is sodium and the chloride. Okay? So number of particles is 2. We have the molecular weight, so we don't need to do much there. What remains is the quantity in grams per liter. So the way you approach that, once again, is you look for any concentration information, and 0.9%, so this is basically normal saline, and 0.9% implies that you have 0.9 grams of sodium chloride in 100 milliliters of solution. But here again, we need it in grams per liter, so we need to solve for the quantity in 1 liter, and a liter is 1,000 milliliters. Okay, so we solve for X, which would be 0.9 grams times 1,000 divided by 100 milliliters. That cancels out, and you essentially end up with 9 grams. So now we have all the information that we need. We put it back into the equation. Milliosmoles per liter is going to be equal to 9 divided by the molecular weight, 58.44, times number of particles, which is 2, times 1,000. So if you do the math, you end up with essentially 308. So we found the osmolarity from the dextrose, and we found the osmolarity from the sodium chloride. The osmolarity for this solution will be the total of those values. Okay, so let's just say total will be equal to 555.56 plus the 308, and that should be equal to 863.56. So we have 0.56 because it says round to the nearest 100 and do not include units. All right, so that's how you would approach this type of questions. We've actually looked at 2 very similar ones, and the take-home message once again is if you have multiple components, you do find the osmolarity of each of them, and then you actually add them up at the end, and that will give you the total osmolarity for the solution. So if you really wanted to go ahead and do these questions again, just head over to the site, the quiz section, and then you can do the quizzes. So now the quizzes are timed, and so that will help you not only know how accurate you are, but how fast you can actually do the questions. And so I encourage you to actually go do that. And if you get them wrong, you can always refer to the solutions. So I still don't see any question in the chat. If you have any questions, just leave them in the comments and I'll get to them as soon as I see them. Oh, that's a nice comment from, I think it's Journaling. Yeah, so thank you for joining. I appreciate you joining this session. And if you have any questions, just leave them in the chat box or in the comments. So thank you so much for watching, and I'll see you in the next video.